the linear map is sort of a big gun when it comes to reasoning about the dimensions of things when you have a linear map around. And since it's such a big gun, it can sort of hide some of what it's telling us about linear maps in general. So let's use the rank nullity theorem to find some consequences that are maybe a little easier to understand, but interesting in their own rights. So let's start with, first of all, the rank of any linear map has to be less than or equal to the dimension of the domain space. Now, this isn't really obvious at all in general, right? Because the rank of a map is the dimension of the image of the map, and the image lives in the codomain, but V is the domain. So, right, it's not obvious that there should be a relationship between these two, but in fact there is. And of course, the rank nullity theorem shows you why. The rank of F plus the nullity of F is equal to the dimension of the domain space, V, but the nullity here has to be greater than or equal to 0, right? Just because it's a dimension, it has to be a non-negative integer. And that means that, well, it means this, that the rank has to be less than or equal to the dimension, right? Because if you add, there's a certain number, positive number, that if you add it to the rank, you get the dimension of V. So that means that the rank had to start out less than or equal to the dimension of V. All right. Next up is that F is 1-to-1 if and only if its nullity is 0. So this isn't totally obvious either. Actually, one way is kind of obvious. So if we assume that F is 1-to-1, so if F is 1-to-1, then, right, suppose we have some element in the null space, right? Well, another element of the null space is the 0 in V. And if F is 1-to-1 and two vectors produce the same output, that means that the two vectors were the same to begin with, right? Because F is 1-to-1. But what we've just shown is that any element in the null space has to be equal to 0. So that means that the null space of F is equal to only the 0 vector. And that means that the nullity of F is 0. Okay, so what about going the other way? If we have a map that has nullity 0, why is it 1-to-1? Well, let's suppose, so we're assuming that the nullity is 0, and let's suppose that we have two vectors, v1 and v2, that have the same output, right? If F is going to be 1-to-1, we have to show that v1 is actually equal to v2. Well, look, we can rearrange this equation. Let's move everything to the left. So f of v1 minus f of v2 has to be the 0 vector in W. But F is a linear map. It preserves structure, so we can write this as f of v1 minus v2 is equal to the 0 vector in W. But this means, right, F sends v1 minus v2 to the 0 vector. That means that v1 minus v2 is in the null space of F, because F sends it to the 0 vector. But we know what the null space of F is. By assuming the nullity of F is 0, the null space of F is just the 0 vector in V. So v1 minus v2 is an element of a set that only contains the 0 vector. That means that v1 minus v2 is equal to the 0 vector, and of course that means that v1 is equal to v2. All right, so we've shown that if F is 1-to-1, the nullity is 0, and if the nullity is 0, then F is 1-to-1. So, right, the dimension of the null space was really capturing how much you collapse down to 0, and if the dimension of the stuff you collapse down to 0 is 0, then you don't do any collapsing. That means it's 1-to-1. Of course, this isn't, well, let me just leave it there. All right, last thing to show using the rank nullity theorem is that all these statements are equivalent. So if we have we're going to suppose that the dimension of our domain space is n. So all of these are equivalent. The first one, restricting the range of f to its image, produces an isomorphism. So we could call that f hat, from f to its image, right? And what f hat does is the same thing as what f does. We're just reducing the codomain. I should say codomain here. We're reducing the codomain, throwing away anything in the codomain that isn't actually taken on as a value. This restriction is an isomorphism if and only if f is 1 to 1. Now clearly if f isn't 1 to 1, you can't produce an isomorphism from it by this restriction. On the other hand, if this restriction does produce an isomorphism, well, f had to have been 1 to 1 to begin with. So right, these are clearly equivalent. We already showed these two are equivalent. So last thing to show is that this is equivalent to the rank of f being n. Well, remember, we have the rank nullity theorem. The rank of f plus the nullity of f is equal to the dimension of v, which we said was n. So looking at this equation, you can see that the rank of f is equal to n if and only if, right, this part right here, the nullity has to be 0. So that proves that these two are equivalent. All right. Last thing is this, that if we have a basis for v, then it's the image of the basis is a basis for the image. What we're going to show is that this one is equivalent to that one. Okay, so let's suppose that the rank of f is n. Now we know that f of beta 1 up through f of beta n span the image of f. And the reason for this is because, right, the betas span all of v, but the image is just everything that happens to v. Well, so the, right, everything in the image is, I guess let me write it this way. Everything in the image is, right, f of something over in v, like this. But then using the preservation of structure, we can rewrite it like a1 f of beta 1 plus dot 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 an f of beta n. So we see that f of all of the betas spans everything in the image. So we know these span the image, right? This isn't anything special about this situation. But if the image is rank n, what we have here is n vectors that span an n-dimensional space, namely the image of f. Well, if you have n vectors that span an n-dimensional space, we've seen that this implies they have to be a basis. So f of beta 1 through f of beta n are a basis. Okay, so right, that proves this way. So now let's prove the other way. Suppose that if f beta 1 through beta n is a basis for v, then f of beta 1 through f of beta n is a basis for the image. Well, if this is a basis for the image, this immediately shows that the dimension of the image of f is n, but the dimension of the image of f, that's what we call the rank, So we know that the rank of f is n. So that shows this way. Right, so all of these statements are equivalent to each other, which is kind of handy because sometimes one of these, in some given example, sometimes one of these will be obvious, but the others aren't so obvious. But if you know any one of these, you get the rest of them for free, which is pretty nice.